Hello Internet, my name is Quinn and this is Blondihacks. I'm hard at work on my Pennsylvania A3 switcher locomotive build and I'm going to get started on the systems now. We're going to get stuck into that. We're going to start with the water system. Lots to do, so let's go. Just like a ship or an airplane or your car, a locomotive has a whole set of systems that all work together to keep the machine operating. Look at your car, for example. It's got a coolant system, it's got an electrical system, it's got a fuel management system, it's got multiple hydraulic systems. You've got your brakes, you've got your power steering. If it's a manual, you may have a hydraulic clutch in there, all separate systems. So there's lots and lots of complexity hiding beneath the surface in all of our machines, and steam locomotives are no exception. I'm going to start on the water system today. Water is moved around the locomotive in various ways for various reasons, but in particular today I'm going to start on the drain valves on the bottoms of the cylinders. There's one place on the locomotive where you don't want water, and that's inside the cylinders. When a locomotive is spooled up and highballing down the main, everything is very hot, very efficient, nothing but superheated, invisible, live steam gas flowing through the whole system, making it all work. Then when that same locomotive needs to come to a stop in a station, let's say, everything's going to start to cool down, including the cylinders, which means any steam coming into that cylinder now is going to condense into water. And that's bad because if the engine starts moving when there's water in there, it's going to hydrolock that piston, potentially break something. You might break a piston ring, you might bend a rod, all kinds of bad things can happen. So a steam locomotive has these drain valves on the bottoms of the cylinders, and when the locomotive's been sitting for a while, the engineer can open those valves from the cab and blow out any water that might be in them. Here you can see 2816 of the Empress just about to roll out, and the engineer opens those valves one last time just to make sure there's nothing but steam coming out of them before he starts rolling. I'm going to make the drain valves for my locomotive today, starting with the valve body. You can see Kozo's design in the corner there for this particular component. It's a fairly straightforward turning job. I'm going to start with this piece of bronze and this piece of steel, with which I'm going to make a drilling jig. These valve bodies are very small and they need a number of accurately drilled holes in them, and they're very difficult to hang on to and get those holes in the right places. So this drilling jig is suggested in the drawings, and it seems like a very good idea, so I am going to make it. What this will allow us to do is hold the valve body in a known position effectively, and these two holes here are the two holes that we're going to need to put in each of the four valve bodies. Also, because we're making four of them, a jig like this is going to save us a lot of setup time. Then there's a tapped hole on the side for a little set screw that's going to hold the valve body in position during the drilling. There's the completed fixture there. I've got this little brass-tipped set screw that will hold it in place without damaging the valve body. You could also use a regular set screw and just throw a little chunk of brass in there, but I happen to have these exotic set screws, so I'll use them. Now we can get on to making the valve bodies themselves. Pretty straightforward turning job. I'll face off the end, as is tradition. When you see locomotives in period movies and such nowadays, you always see them sitting in the station with steam billowing out of everywhere. It's actually not what steam engines look like most of the time. You don't want steam billowing out of everywhere because that's wasted fuel. You used fuel to make that steam, so you want to contain it. The only reason that steam is ever billowing out of a locomotive generally is the drain valves on the cylinders being open when the locomotive's been sitting for a while and they're trying to keep water out of the cylinders. I turn a smaller diameter on the end of the piece. This will become the threads that will thread the valve body up into the cylinders. Next, I drill the actual water passage that will allow the water to escape from the cylinders. This is a very tiny hole that goes very deep. It's what we call a high aspect ratio hole. The ratio of diameter of the drill to depth of the hole is very, very high. And that means I need to do lots and lots of chip clearing, because the smaller the drill and the deeper the hole, the less efficient drill flutes are at clearing chips. And then I put the threads on the end. And finally, I want to undercut the base of those threads so that the valve body will thread flush up against the bottoms of the cylinders. As flush as they can, of course. The cylinders are round and this is a square surface, but it'll be close enough. Now I want this to be accurate because this is a registration surface for the valve bodies, and you'll see why that matters in a minute. So I made a little test thread in a free area of the drilling jig and used it as a thread checking jig to make sure that my undercut is deep enough that I can thread fully square up to that shoulder. And the undercut needs to be a little bit smaller in diameter than the minor diameter of the thread, but you don't want to go too far because the material is thin and it would be very easy to weaken it. So I just go a little bit at a time and check it. I'm very careful about that because I absolutely have had plumbing fittings break because I went a little too deep with the thread relief. And because someone always says it, yes, if you use a round profile instead of square, then you don't get stress risers caused by sharp corners. Fun fact though, stress risers causing a part to fail definitely matters if you're making drive spindles for a 797 Caterpillar mining truck. The amount that it matters on a scale model plumbing fitting is 0. That's all the operations I can do from this setup, so I'll part this off. And, oh, bad Yahtzee. Oof. Yeah, about once every 100 parts or so, if I'm doing a small diameter part close to the chuck, it flies off the parting blade at a crazy angle and gets snagged by the chuck jaw and mangled. And that's what happened this time, so I got to make that one again. The next job is to put the cross holes into these parts, but they have to be clocked correctly to the threads, which is extremely difficult to do. It can be done, but it's much easier if you can to just make the threads first, install the parts where they're going to go, in this case on the cylinders as you see, and then figure out where the cross holes need to go relative to where the threads happened to end up being clocked. So I've got parallel up against the bodies of the valves, and I'm marking the point where the outside of the curve just touches them, using that parallel. The height of those valve holes was then marked on the surface plate with the height gauge, and I can bring those over to the drilling jig now and line up the 2 crossed scribe lines for each of those valve cross holes on the drilling jig. Of course, what this means is that each valve body now is tied to a particular position, so I've stamped the bottoms of them with numbers so I know where they all go, because the thread clocking is certainly not going to be the same on all 4 of them. This larger drill is the through hole for the valve spindle. This is not a tapered valve like you often see on model locomotives. This is a cylindrical valve spindle. So there's a cross hole that goes all the way through. This is the pre-drill size for the reamer that will define the geometry of this hole. And then upstream of that, there's a much smaller hole, which is the outlet of the valve, and it connects to that lengthwise hole that we drilled earlier on the lathe to make the actual L-shaped passage inside the valve. So this gets drilled just down to the center line of the valve body to connect and form the little L passage. You can always check if you connected your internal passages correctly by putting a little air on one end. You should be able to get a chip fountain, and we did, which means those passages connected. When designing fixtures, make sure you have a way to get the part out. In this case, I drilled the main hole all the way through so I could tap the valve body out from the back. After that cross drilling, there's burrs on the part that are locking it in to the drill fixture, and you won't be able to just pull it straight out. So it might need some persuasion. There you can see the 2 cross holes. I threaded them back into the cylinders to check the clocking of those holes, and it looks correct. That seems to have worked. So result there. At this point I could remake one of them if I needed to, but they all looked good. Now I need to do some additional operations, but the valve bodies are now a weird size. So I dug through my collection of aluminum adapter collets that I've made over the years, and I found one the correct size, and I'm going to try to hang on to these like this in a collet block. And what I need to do now is ream those cross holes. I couldn't use the drilling jig for that, of course, because the reamer is going to open up the hole, and the drilling jig has the pre-drill size in it. So I thought, well, if I can line these up in a collet block, both on rotation and XY position with a gauge pin in the spindle, then I should be able to run a reamer through there and open them up. These valve spindles are a very specific 100 thou in diameter. That is a very unusual size in the imperial world, so I had to special order these exotic reamers, but I was proud of myself because I was using precision ground rod, so I wouldn't have to do anything to the valve spindles themselves. They'll just fit right into the... Oh no. Yeah, the precision ground stainless rod I have is actually 102. Why is it 102? I don't know, but it is, and I didn't order anything else, so I'm going to make this work anyway. I'm going to ream these out with the larger of the 2 reamers that I ordered. I ordered the nominal size and an oversize just in case. So I'll use the oversized one and I'll massage the spindles to fit. You'll notice an extra slit has appeared in the adapter collet. I normally use these adapters in my ER collet chuck on the lathe where they work great, but these 5C collets only have 3 splits in them and they don't squeeze all the way around as nicely as an ER collet does. So I had to add a slit to my adapter to get them to compress properly, but it did work eventually and got the job done. I will say that worked okay, but I wouldn't do it that way again. I think I would make a special reaming jig for that operation next time. It would actually have to be 4 reaming jigs, 1 for each hole, because every time you do the reaming, it destroys the jig effectively by opening up the hole in the jig and the part. But that would have been probably easier than fussing around with that collet block like I did. But anyway, back to the lathe now, using the same adapter collet. I'm going to turn down a nice little detail feature on the bottom of the valve body using a tool bit that I found in my bin. I don't know where it's from, some auction or something. But it has an angled grind on it that will allow me to put a nice little taper detail there on the bottoms of these valve bodies. That seems to have gone just fine, so that is looking pretty good. Times that by 4, and we have our 4 valve bodies. Time for the spindles that go in those holes now, and this is, as I said, made from precision ground stainless bar stock. This is the stuff that I used for the handrails way back on the tender. Start by facing off the end. And now I'm going to pull it out of the collet a ways because I need to turn it down a little bit. But I'm not actually going to use a turning operation for this. I'm going to do it with emery. The reason being, I only need to come down about 1.5 thou on diameter, so it would be an incredibly light cut, which isn't going to work very well on stainless anyway. And there's a lot of stick out on this part for its diameter, so it's not a rigid setup, which is also going to make any kind of turning cut very problematic. This does take some time, but one way I found to manage this that worked really well was to use a stopwatch. I determined experimentally that with fresh emery, it's about 10 seconds per tenth of diameter reduction at 800 RPM on this particular material. So I would go, a minute or 2 at a time on the stopwatch and check my progress. And I was test fitting on the valve spindle as I went. Each of these is custom fitted to a particular valve body because this has to be a reasonably good gas and pressure seal, but there's no rubber O-rings or anything in this assembly. It just has to be a metal-on-metal seal. And that is honestly very difficult to do, especially at this tiny size. So that's why I'm custom emery fitting each spindle to each valve body. On this one, for example, you can see that I landed at 100 and 1/10. So 1/10 over nominal was where this one wanted to be for a perfect fit. Now I used those oversized reamers, which are 5/10 over. So ostensibly that's a 4/10 clearance, but assuming that reamer cut perfectly nominal, which it probably didn't. But anyway, that seemed to work. I made all 4 spindles that way, and then I needed some tiny E-clip grooves at each end of each spindle, which was done with a magnifying glass, as you saw there, and a little test fit of the E-clip to make sure it's a good fit. You can see I've choked up on the part now for the grooving cuts because these are high tool pressure. And those E-clips are stainless as well because, of course, all this stuff's going to get wet. Well, there we go, 4 valve bodies with their custom-fitted spindles. I'm being very careful to always keep them together because each one has been meticulously hand-sanded for as perfect a fit as I can humanly get on each one in the hopes that they will seal. We'll find out in a bit if they do. Now, each of those spindles needs a cross-hole drilled through it so it can actually be a valve and not just a stick in a hole. I added a new section to my little drilling fixture. That's like 6 jobs now this thing is doing. This allowed me to perfectly center the cross hole between the 2 E-clip grooves, which will center it on the valve body. Smooth jaw Knipex pliers for the win. That is looking pretty good. Those cross holes look excellent. Jig for the win. Now, after doing that to all 4 valves, I want to see if they are actually going to seal. So I made up a little adapter fixture for my low pressure air line, and I'm going to thread each of them into this and test them for pressure tightness. Moment of truth. I was very nervous at this point. I'm putting 20 psi on those to test. Let's see what happens. It might not be closed right now. I don't know what position it's in. So I'll turn that until the noise seems to stop. Okay, looks good. Let's get some soapy water on there and see how much it's leaking. And there's a lot of bubbles coming around the thread, which is not surprising. There's no sealant on that. And yeah, there's some bubbles coming around the spindle. I mean, it's not a perfect seal. I didn't expect it to be, but it's actually pretty good. It's honestly a lot better than I thought it would be. Here, I'll give you the sound so you can actually hear it working. I'm pretty pleased with that. I mean, it's definitely bleeding down a little bit. It's holding 20 psi, but it will bleed down. And of course, the locomotive's going to be running at more like 80, but it's not going to hold that. And I didn't expect it to, like I said. I'm amazed. They honestly work as good as they do. These are as good as I can possibly make them, so if these aren't good enough, well, then we're just going to have to live with some seepage and some dripping. That's just steam locomotives for you. Making stuff accurately enough to work absolutely flawlessly at this tiny scale is exceptionally difficult and frankly outside my ability. Now, some would say that the design of these valves is not very good for what it's trying to do. I will say that in the book, Kozo comes down firmly on the side of cylindrical through spindles like this seal better than tapered cone style valves do. I don't know enough about model valve making to have an opinion on that either way, so please don't shoot the messenger, but that is what he says, and so that is why he designed his valves this way. The next piece to make are the little crank arms that allow the linkages to open and close these valves from the cab. For that, I've got this piece of stainless bar stock that I'm going to use. Unfortunately, I was not able to source bar stock the nominal thickness of these little crank arms, so I'm going to have to machine this stuff down, make my own stock. That's a bit of a sub-project all of its own. I'm going to start by cleaning up the edges of it, not because they are reference surfaces, but because having perfectly flat parallel edges allows you to get a very good grip on the part in a milling vise. And that's going to be important because we're going to be gripping on very, very little of this material. So I've got an adjustable parallel in there, and I'm getting it set just right so that I've got just the minimum amount of vise jaw in there. I'm going to be thinning this down to 1/16 thick, which means I need to have maybe 30 thousandths in that vise jaw. That's all that's going to be holding it. And that will allow me to machine down to 1/16 thickness without, of course, touching the vise jaw. It's also why I machined the sides parallel to ensure a good grip with so little material, and also why I'm doing this on the mill and not on the shaper, which might be more fun. My vise on the mill is a lot better. I trust it a lot more with a tricky operation like this, and the tool pressure from a milling cut is a lot less than the shaper would be banging into this, so I would be asking a lot of the vise trying to hold on to 30 thousandths of material with a shaper banging into it. I did get away with this, however. I probably shouldn't have, but I did. Another way to do this, if you need to go even thinner, for example, is to leave extra material on the ends and put holes in it and screw it down into a fixture plate. And then you can machine it very, very thin if you need to. But this is about as thin as I would go in a vise setup, but that did work, so I'm happy with that. I need 4 of these little crank arms, so I've calculated a distance between all the sets of holes on each of the crank arms that will give me plenty of bandsaw, blade kerf, and finishing cut range between each of the parts. That'll allow me to drill all of the holes in one easy setup, while the stock is easy to hang on to. These all get drilled and reamed to 2 different sizes at each end of each arm, like so. Then on the surface plate with the height gauge, I marked a halfway point between each pair of holes, which then allows me to cut them apart. Again, I've left plenty of room there for milling to final dimension. To do that milling, I'm using this setup. I've got 2 pins, one in each hole, to make sure that my cuts are parallel to the center lines of the holes. However, the holes are different sizes, so I've got shim stock under the smaller one to make up the difference in radius. To get the dimension on this cut, I used a depth gauge from that machined surface to the top surface of the pin, and a little bit of math tells me how deep I need to go. It's fiddly with that depth gauge, but I only have to do that once for all 8 cuts, because I just zero the DRO there and cut all 8 of them to the same depth, and they'll be the same. And that seems to have worked well. The cuts look parallel, they seem to be parallel to the center lines of the differently sized holes. And on to the next step, which is rounding the ends, which I did on my little belt sander fixture. Makes quick work of that. These are about as straightforward as locomotive parts get, but the small size and the challenging material, stainless, made them quite an adventure to make. The next step is very tricky. The valve spindle needs to be clocked correctly to these crank arms. All 4 of them need to be at 45 degrees to the cross hole, and all 4 of them have to be the same so that when the linkages activate all 4 valves, they all rotate 45 degrees into the open position, and all 4 of them open. Now, the smart way to do this would have been to do the soldering of the arm onto the spindle first and then come up with a jig that would allow you to drill the cross hole at a 45 degree angle relative to the arm. I didn't think of that, so I ended up doing this convoluted thing instead, where I put a gauge pin through the cross hole and then arranged the gauge pin to be at a 45-degree angle on the surface plate, and then scribed a little mark across both parts for the correct clocking. That was a really ridiculous way to do it. Do not recommend it. It did, however, work, so I guess that's something. Now the soldering is tricky. The drawings recommend this fixture, which I took advantage of. It's a piece of spring steel with a notch cut in it that fits into the E-clip groove. Then I've got a shim that's the correct thickness to space the arm above that E-clip groove and hold it in the correct position. Line up my scribe marks to get the clocking correct, a little bit of flux, and the tiniest piece of solder I can manage to cut, and in with the heat. I'm keeping the torch way, way back, just feathering it in there very gently, because these parts are so small I don't want to overheat them, and I don't want the wind of the torch to blow everything out of alignment. So keeping the torch way back worked. This would be a good job for something like a jeweler's torch, and I actually have one. A viewer sent one to me many years ago. Thank you very much. I'm sorry you haven't seen me use it. It needs special oxygen and acetylene tanks, and I haven't managed to source those, and so that's why I haven't used it. Next, a little pin gets soldered to the other end of that crank arm. I made these pins off camera. It's a straightforward turning operation. I used this kind of angled chunk of ceramic as the fixture to hold this pin at the right height. That, combined with a bent piece of shim stock below that, allowed me to have quite fine control of the exact height of the pin in the crank arm. It had to be held at just the right height so that the pin was flush with the back of the arm. And then again, flux and again the tiniest piece of solder I could manage, which is still too much. Each of these parts had a big blob of solder on the top of it at the end that I had to file flat, but I just literally can't cut a smaller piece of solder than that. And again, holding the torch way back. Now you might be thinking, hey, aren't you going to damage the earlier solder joint? I was also worried about that until the second one of these that I did, I actually got the clocking wrong on that spindle crosshole that I talked about, that ridiculous gauge pin setup that you saw, and I had to try and desolder it, and I was not able to. I ended up destroying the pin trying to desolder it, and I got to make that valve spindle again. I was able to salvage the arm, but not the spindle, so I made 5 of those valve spindles. So that's why I wasn't worried when I came to do those other pins that it was going to damage the earlier joint, and it didn't. Bunch of cleanup later, and there is the little crank valve spindle assembly. My goodness, those were challenging to make. Honestly, this whole set of parts really kicked my butt. It was one of those times where seemingly everything went wrong, but I had to redo stuff a bunch of times. I broke a couple of tools. My fixtures weren't working right. Everything went wrong. It was a disaster, but sometimes you have days like that and you just got to persevere. I think these are all going to work. Like I said, they're definitely going to leak, but that's okay. It's a steam engine. The first 3 rows will get wet, and they certainly look the part. Here they are on the locomotive. I've installed the cranks on them backwards so that you can see what they look like, but in final installation, the cranks actually go through the bodies from the other side, so the linkages are on the back, and of course, so the linkages aren't blocking the outputs on the valves. But at least you get to see what it looks like kind of from the inside, as it were. You get a better sense of how they're going to work. There's 4 drain valves, made with love and slightly leaky, just like me. I hope you enjoyed watching me make these little guys. Lots more to come on this system, but thanks to my patrons for making all this happen, and I'll see you next time.